in my programming class, and every time, I mean, I'm always working on some sort of physics stuff. He's like, "Ooh, I'm so excited for you to take D4." He's like, I love it.
That's cool. Okay, well, so I finally got this equation sheet, so I might update it as we go. But some very similar thing to this is, I guess I'll just give you on all the exams so you can get used to just working from this sheet.
Thank you for making that.
Yeah, sure. It's on D2L now, and I guess, for the test on Friday, we will be up through this control volume equation. So I guess I'll give you all these equations, but just keep in mind that all of this stuff, starting with the Greek letters, is the next topic. Okay? Any questions about that? Look at all this stuff coming. Oh, and actually, that's not true. A lot of this ideal gas and incompressible stuff is relevant for the test, but none of the entropy stuff. You can see like a lot of the ideal gas stuff is entropy stuff. Isentropic processes, that's all entropy. That means the entropy doesn't change. But
how did I miss that C is du dt?
Only for incompressible materials. Yeah, that's an important thing. So it's good you're seeing it now.
Change in internal energy.
Where's the word right there?
Specific internal energy, right?
Yeah.
Got it.
And so that's the thing that lets you calculate the change in internal energy for any given change in temperature.
Yeah, because that C's got the mass specifics wrapped up into it.
Yeah. I mean, does it use? Yeah, it has a bunch of stuff wrapped up into it, and so it lets you find a relationship between a change in temperature and a change in internal energy. So, like, you could calculate, like, if you have liquid water, 2 kilograms of liquid water, and you add, you raise the internal energy 400 joules, you could calculate what the change in temperature would be.
But I guess I've used that. I don't know why looking at that, I was like, huh?
Yeah.
I'll say a lot of these ideas haven't really clicked for me until like this last week or so. And that was one of them.
Yeah. Yeah, man, I try to go back and outline what we've done so far every once in a while. I think it also is helpful if you do that for yourself pretty regularly and write out lists of equations for yourself. It's just so many different things, and like none of them, it's like this class, I don't think, like, it's not usually like a real subtle, hard to understand thing to apply each individual equation. It's just more a thing of like cataloging all these equations in your head and how they, like, knowing like, okay, this problem has this, so here are the equations available to me, And so just like making lists, making outlines is really helpful in a class like this, I think. Okay, so that's the equation sheet. So the big news is exam 2 is on Friday. And the topics for that are everything. So be ready for stuff from earlier too, but up through control volumes. So there's none of this second law or entropy stuff. Anybody have any questions on problems or anything about the test? I'd be happy to do anything like that.
Nothing immediately apparent.
Okay. So then the next thing I want to do is I want to go through a couple of questions from the homework that was assigned for today. It looks like, so I assigned numbers 1 through 4. 1 and 3 had solutions posted, so let me go through 2 and 4. So
And
this,
actually, on number one, I sort of came to a different conclusion on one.
Oh, yeah?
Than was in I think it was 1A. Let me look at it. Or no, not one. I said one of them was impossible. Oh, it was 3B or 3A. Sorry.
oh, 3A.
Yeah.
Okay.
Whereby I think it was by calculating the eta and then eta ideal. What?
Mm-hmm.
Where I came up with a higher eta.
Okay.
Like my eta was greater than eta ideal, which should mean it's impossible, right?
Right. Yeah. And I said it was possible.
And you said it was irreversible, I think.
Okay. Well, let's do that one too. Let's so let me start at number 2. So this is a power cycle, and the way a power cycle works, we have the high temperature reservoir, the system, and the low temperature reservoir. We have QH coming in from this TH. We have QC going out to this TC. And then we have work being produced. And if you think about the first law, this is a cycle. So over a cycle, there's no change in energy for the system. And so the stuff going in and out have to balance. And so that means that QH has to be equal to W plus QC. And we also, the performance, okay, we're given these temperatures. So the performance, the efficiency of a power cycle is 1 minus QC over QH. And the ideal efficiency, if this cycle is reversible, is 1 minus TC over TH. So this is really, I think this problem is just a matter of calculating these things and comparing the efficiency to the ideal efficiency.
So if I did QH over TH minus QC over TC, is that like similar to this? Just
Say it again. You did what?
What is that? Is that change in entropy? I don't know. This is just what I have. QH over TH minus QC over TC.
So for this one, it's simpler than that. You're just going to use these equations.
So was that wrong? Because I guess I came up with on the first one, I came up with a negative number. And so because I came up with a negative number, I said irreversible.
Right. That's correct. Yeah. For these problems, it's not asking you to think about that stuff yet. This is like a step before you start thinking about that integral definition of the Clausius inequality and that definition of entropy. So all this is asking you to do is say, okay, so for part A, the efficiency of this cycle is 1 minus 300 over 600. That's 0.5. The ideal efficiency, we're given these temperatures. So that's 1 minus 300 over 1,000, which is 0.7. And so for each case, so since the efficiency is less than the ideal efficiency, this is irreversible.
Okay.
And I don't think there's much to it than that on any of these. Sometimes you might have to use this first law equation, this QH is equal to W plus QC. So for the second one, let's see, QH is given, the work is given, QC is given. Oh, another thing, I guess it can ask you to check. So you can also use this first law to verify whether it's possible. This has to hold, you know. So like, for example, for part C, these numbers aren't possible because W plus QC is greater than QH.
Okay.
So that's another thing, I guess, to check. But mostly you're just checking these ratios. So for part B.
So I guess if you were looking at making an order of operations to check these, first you'd want to check that first law.
Yeah, I guess that's true.
Probably
Yeah,
the easiest thing to
it's
check,
easiest.
right?
Yeah, you can just do that visually, and then do those calculations. I think that's probably a good way to do it. Honestly, I probably won't put any of these on a test because they're so short and
Rudimentary.
yeah. But it's just supposed to be kind of. I assign this stuff just to try to stick it in the back of your mind somewhere. Okay, so for part B, eta is equal to, what do we have? 1 minus 280 over, was it 400? So that's 0.3. So again, that's irreversible. And
no, it's 0.7. Oh, 1 minus.
Yeah. And then for part C, QH is not equal to W plus QC. And so this is impossible.
So wait, what's eta ideal and B?
They're all the same. It's all just talking about the same system with these two hot and cold reservoirs.
Okay. So yeah, there really isn't necessarily a correlation at all between the entropy and between these eta.
Well, no, you're right that you can use the entropy to do the same thing if you have the right information. Well, I guess not the entropy, but the Clausius inequality.
So, and is the Clausius inequality like comparing entropy?
Clausius inequality is not entropy. It uses that same form of thing, that same form of integral, but the Clausius inequality is doing that for actual cycles, and it has to be cycles. Whereas entropy is doing that for not necessarily cycles and for like an idealized reversible, internally reversible process. Okay, so number 3, you said you got something different than I did. So we have this thing at steady state. Steady state, just like a cycle, means that, so we're doing all of this in terms of differential forms, but steady state means that the time derivative of energy is 0. So we have, for this one, we have a temperature of, it said 1000 Kelvin. Oh, let me paste this in here. Okay, so we have a high temperature reservoir at 1000 Kelvin. And a low temperature at 300 Kelvin. And it's a power cycle, so we have heat QH coming into the system, heat QC leaving the system, and work W being done. And the first law, so in this case, for the differential form in steady state, we have that QH dot is equal to W dot plus QC dot. And we're really doing the same thing we were in number 2. So first, we can check the first law. So QH dot okay, so all this gives is, so we don't have any information where we can check the first law. So all we can use is the ratios. We know that the ideal efficiency is 1 minus QC dot over QH dot. And so that is 0.7. And then we can do the actual efficiency is 1 minus QC over QH. QC is 100, QH is 500. And so this is 0.80, so this is impossible.
Am I crazy?
Yes.
And a lot of
Yeah.
Lock them up.
Because that is the answer I got, but okay. No, I'm good.
Okay.
You,
Yes.
you just figured them out in reverse order.
Oh, okay.
So for ideal, we just use like it's the same values as the temperature.
For the ideal, in place of all the heats, you input the temperature. You use the temperature. So that is the ideal efficiency that you can have for a cycle with those reservoir temperatures.
Is that because all of the heat goes to temperature changes?
It is because I do not have that derivation at the tip of my brain, but it has to do with defining. So the way they define a Kelvin temperature scale is in terms of a reversible cycle. And so it all gets pretty murky to me.
It sort of just spits it out at the end.
Yeah, right. But they go through this long derivation, and then that's what you get is that the ideal, the best you could do at those temperatures is, what you get from replacing the heat in the performance measure with the temperatures of the reservoirs.
That makes sense. If there's no
Yeah.
heat going to other places
Yeah.
other than temperature changes.
Yeah. I don't know. I can't say I have but I mean, if you have whether it makes mathematical sense or not, if you have a way that helps you remember it, I'd say just stick with it, Yes.
You could do the same with the first law equation as well, like substitute the temperature and put
With the first law equations, could you? It doesn't make sense because of that W.
okay.
That W doesn't really have any temperature analog, Okay, so how about B? So in this case, well, we know that the first law says QH dot has to be equal to W dot plus QC dot. For part B, you can see those don't add up to 500, so this doesn't hold. So this is impossible. And then for C, this time we're not given QH, but we can use W dot and QC dot to calculate what QH must be. So QH dot is equal to 350 plus 150. So 500. And now the efficiency is 1 minus the QC 150 over 500. I'm being pretty sloppy with my units and stuff just because the units and anything you're multiplying by it are going to cancel out in this ratio. And you get 1 minus 0.7. That is equal to, I think, the ideal. So this is a reversible. And then for number 4, so we don't know the temperature at the boiler. I'll call that TH. And then we do know that the cold reservoir is at 280 Kelvin. And we know that this cycle has to develop 40 kilowatts of power. So our W dot is 40 times 10 to the third watts. And our QC dot is per minute. That's a pain. Okay, so, well, just divide that by 60. That's not so bad.
16.67,
Okay.
right? I think.
Yes, that's right. So QC dot is 16.6 repeating times 10 to the third watts. And so we know that QH dot has to be equal to the sum of these two. So that's 56.6 repeating times 10 to the third watts. So that
figure out eta from there.
Yeah, I guess so. So by giving these two values, we're locked into what the efficiency has to be. So this is equal to 1 minus 16.6 divided by 56.6.
0.705.
Okay, so 0.705. And then we can say the ideal is 1 minus the cold temperature divided by the high temperature. And this is equal to 0.705. So 280 over TH is equal to 0.295. And so TH is equal to 280 divided by 0.295. And that is 949.15. Any questions about any of those?
Is this somewhat representative of what the future problems are going to be?
All of the problems in this set are that. Yeah, but I mean, there's only 2 more of those.
Well, I guess I meant, like moving forward, is it kind of more of
Based on.
Right.
This makes more sense.
Not really. This is just kind of,
Giving you hope.
yeah, maybe you're right. Yeah, I would say not really. Jay, you have a question?
Yeah, with the test on Friday wouldn't have.
It has none of this, right? It only goes up through the control volume stuff. Okay.
That's really helpful though, to kind of
Yeah.
visualize like how
Mhm.
energy's moving around.
Right. Yeah. So what was I going to do next? I was going to do an example problem of the next set of problems, which is Clausius inequality. So remember the Clausius inequality from last time said for any cycle, and by any, I mean we're not talking about any kind of perfect efficiency system. we know that the integral over the cycle of delta Q over T, if you go all the way around the boundary, I wrote it last time is less than or equal to 0. We can also write this as negative is equal to negative sigma.
7 Boltzmann constant?
No, it's a new sigma.
Okay.
Yeah. That would be amazing. Where sigma is 0 for reversible, and otherwise sigma is positive. We're going to be regularly using this this variable sigma to calculate sort of an amount of, you can think of it as kind of like an amount of entropy that's being created. So we're not talking about it yet that way, but we're gonna be dealing with it that way, just as a way to sort of measure how much inefficiency you have in your system. Okay, so let me do an example of the kind of problem you'll do for Clausius inequality. So let's say that a system operates a power cycle. And so we have our TH, our system, and our TC. And as always for these, it's a cycle, so we know QH is equal to W plus QC. And we're told that QH is equal to 1,000 kilojoules. And the temperature is 500 Kelvin. And in the exhaust, we lose an amount of heat QC. Well, we don't know how much that is, but we know that the temperature at that cold reservoir is 300 Kelvin. And we want to determine this value of sigma if we know that the efficiency is 0.2. Okay, well, the efficiency is 0.2. We don't know anything about the work or anything like that. We know that if this was a perfect cycle, if it was a reversible process, the ideal efficiency would be 1 minus 300 over 500. And so that is 0.4. Okay, we know that. And we know that using the see. So we know that using that definition, that Clausius inequality, delta Q over T, if you take into account all the places where heat is transferred, this would be equal to 0 for the ideal case, the reversible case. Does that logic make sense so far? You understand? Okay, so where do we have heat transfer? We know that we have coming into the system, we have 1,000 times 10 to the third joules divided by a temperature of 500. And then we're losing an amount QC at a temperature of 300. And this has to be equal to 0. And so now we're just calculating that QC. So QC is equal to 800 kilojoules.
Now, is that like a QC ideal?
So yes, this is the QC if this thing is reversible. QC.
What case would it be irreversible?
To be irreversible? That would be, so I gave you that list of the 7 things that contribute to irreversibilities, the 7 irreversibilities. And so you just have combination of those things.
But it doesn't matter in terms of if you don't get the same as the ideal, that's impossible. Or below the ideal, no.
Right. So
So couldn't we calculate what QC, the real QC is, since we were given the true eta?
we're given the true eta.
So could we say 0.2 is equal
Oh, yeah.
to 1 minus?
Yeah, right. Why am I even doing, yeah. So QC, yes, thank you. Let me make sure that this is what I said it was. 1,000. Okay, so no, this is not, yeah, right. So this is, what is it?
600?
Is it? One?
Well,
Oh,
it's
yeah.
just 2 minus
You're right. Yep.
2.
So 600 times 10 to the third joules. This would be for a reversible. That's not relevant to what it's asking, turns out. So, right, exactly. So what we have is that eta is equal to 0.2, and that's equal to 1 minus QC over QH, which is 1,000. And so this tells us that QC is equal to 800 times 10 to the third joules. This is in the actual case. And you can see that, so if you had perfect efficiency for this system, you would be losing less of that energy to the exhaust. In a less efficient system, you're losing more energy to the exhaust. And now we can use this with the Clausius inequality. This is equal to negative this variable sigma. And so we have 1,000 times 10 to the third over 500 minus 800 times 10 to the third over 300 is equal to negative sigma. And you get that sigma is equal to, I got 666.6 repeating joules per Kelvin. Yeah, right. Yeah. So anyways, yeah, you have a couple of equations and you just have to see the path to, combining these equations to get the variable you're looking for. You did that one better than me.
It was a team
Sucks.
effort.
Yeah, right.
There was like a voice in my head telling me something, but I didn't have,
Yeah.
I'm not there where I
Right.
could ask a question.
Right. Yeah. So we knew the efficiency. That let us calculate our Q sub C. I mean, I guess we took that detour that I didn't mean to take, but
But wait,
it is helpful to
could we
see
have
that those
used-
exhaust values are different.
Could we have used that 600 number to get there too?
I don't see it, but
Well, yeah. I feel like there's some relationship between 600 and 800 that involves that. But
Mhm.
maybe.
Find a ratio?
I don't know. I don't see it, but maybe. Okay, the next thing we're going to do. So this is just like a kind of problem that you're going to have to do on the next assignment, 1 or 2 problems like this. And then the next big thing we're going to get into is the TDS equations. So these are always applicable. There aren't too many equations that we've had that are where that's true. And you use them to find relationships between changes in entropy, I guess it's specific entropy, and changes in other properties. And the two TDS equations are TDS is equal to du plus PdV And the second one is TdS is equal to dH minus V dP.
So there's no like, something has to be constant.
Exactly. There's nothing like that, although you do have to have simplifications in order to compute those integrals.
So is that like a change in enthalpy? Right? I mean, that just like looks, isn't enthalpy U plus PV?
So that is, okay, so a change in enthalpy.
Or like a one-dimensional, like a change.
Yeah, there's
one of either.
I do not think that there's any kind of intuition really to have about what that means. This change in enthalpy really would be du plus pv, and then you'd have to use the product rule. So this is equal to du plus dp vdp plus p dv. So that would be like a change in enthalpy. You can use, you can actually now rearrange this and you get that dH minus VDP is equal to du plus PDV, which sort of helps you remember what these two forms are, but
Neat. That's pretty cool.
yeah.
So it's like sort of, I don't know.
Yeah, I mean,
I guess that just lends,
yeah.
it lends credence to the
Right.
fact that enthalpy is sort of just like this mathematical.
Yeah, but how those come out to be TDS, I don't know that derivation.
And is that T temperature?
Yes.
I just keep thinking TES reports.
Yeah, right.
Killing me.
Yes. Okay, so let me show you a simple calculation with that. I think I have something like that. So here's an example. So calculate an expression for the change in specific entropy for an incompressible material. So I'm going to start with, we have TDS is equal to, I'm going to use the one that says du plus p dv. Okay. And I'm going to use this form because we have two useful things here. We have that dv is equal to 0 for an incompressible material. That's like the definition of an incompressible material. And we also have that, what you were just mentioning, Colton, at the beginning of class, that C is equal to du dt. So we can replace this du with C times dt. And now, so we have this equation that says TdS is equal to C dt for an incompressible material. Now divide both sides by T, and you get ds is equal to C times dt over T. And now we have a form that we can integrate. This is from state 1 to state 2. I'll pull the constant outside of this, and this is from state 1 to state 2. And what we get is that the change in specific entropy is equal to C times the natural log of the later temperature over the earlier temperature. And that's actually an equation that's in that equation sheet. So if you have an incompressible material and you know the temperatures and the specific heat, you can always calculate the change in entropy.
But that's pretty convenient, like
Yeah.
in practice.
Right. And this, you could have an incompressible material, say liquid water, and do this for 2 temperatures, and then look in the table for temperatures and pressures, and you'd see that this is a really good approximation. But I guess the main thing that I want you to take from this is often you can calculate relationships between properties like this, but we really can only do it in cases where some of these cancel, or some of these variables as functions of other variables or something like that. Okay.
You can basically only do it if you have a function for either little v or little p, right?
That's right. You need to either have a function, so you either need p as a function of v or v as a function of p, and and then you could calculate those integrals.
And either solve for little u, little h, or little s.
Mm-hmm. Right.
Cool.
But usually we're going to do it to solve for delta S. Any other questions right now? Okay, that's all.